Now we are going to proceed with the calculation. This is the very simplest part of what we can say, because you are done a lot of calculation questions. So you just have to follow that how to get. He says that from your accurate results, and as I mentioned, the consistent results are considered as what your accurate results. So use those, like the first one, 25 point I forgot what was the value there, 25.60 plus 25.50. These were the two results which are consistent, as they have a gap of 0.1. divided by 2, you will get the final reading, or the accurate reading, which is 25.55. Understood? So this is the volume of the FA1 used, FA2 used. Now go back and check what was the concentration of FA2. The concentration of FA2 we are going to find, and here he says that concentration of FA1. Okay, let me check what he's saying. Required, so 25 centimeter cube of Fa5 required this amount of Fa1. We are going to check the concentration of Fa1. See, concentration of Fa1 is 0.02, and it was potassium manganate. Okay, so keep that. And now, as we know the concentration which is 0.02, and the volume we titrated from and we got from the burette, so we can easily find the number of moles by using the formula N equals to C times V. C is the concentration, which is 0.0200, multiply by the volume you obtain, which is 25.55, and divided by 1000. Why? To convert the volume from cm cube to dm cube, and when you do this you will get the answer. Okay, so let me calculate using my calculator, and here he says 25.55 divided by 1000 multiplied by 0.0200, so the answer is 5.11 times 10 raised to the power minus 4 mole. Unit is already there. Okay, now from the balanced chemical equation, remember that what was the ratio of the iron ion, which is Fa2, and ratio of the manganate ion which is Fa1, we calculated just, is 1:5. So if we use the balanced chemical equation, we can deduce the moles. Okay, so he says that calculate the number of moles of iron 2. So we can say iron 2 ions, the ratio is 5, whereas the manganate ions has the ratio of 1. So when we have this ratio, and originally the manganate volume we calculated was 5.11 times 10 raised to the power minus 4, what should be the moles of iron 2 ions. So okay, so just multiply it by 5. So the answer, multiply by 5, we got 2.55 times 10 raised to the power minus 3. Again, unit is given. Then he says that calculate the concentration. So we are going to use the same formula, N equals to CV. Just rearrange the formula, you will get that concentration is mole divided by the volume. But remember, volume should be converted into the dm cube first. Okay, so the moles we calculated was 2.55 times 10 raised to the power minus 3 divided by volume we pipetted, that was 25.0, and divided by 1000. Okay, so what we are going to do, we are just going to 25 divided by 1000 and then do. Okay, so this is the answer, which is 0.025. Now 2.55 times 10 raised to the power minus 3, divide this by, let me calculate, by 0.025. So the final answer I got is 0.102 mole per dm cube. And keep that in mind, I just calculated. I just show you the procedure how to do this, okay? But my reading was just the what we can say as assumed, okay? I just assumed that that was the volume of the pivot usually, so it may differ according to your readings, okay? Just stick to the pattern and just stick to your values. Finally, what he says that Fe2 was prepared by dissolving hydrated ammonium iron 2 sulfate. What I said at the beginning, that iron 2 ion usually taken from the Mohr salt, which is a double salt containing ammonium iron 2 sulfate, ammonium ion and iron ion, 2 of the cation and 1 is the anion. That is why it is called as a double salt. The formula is this one, which is hydrated now, okay? Then he says that dissolve in water, calculate the mass of the salt that would have to be dissolved. So we are going to use the formula N equals to the given mass divided by the molar mass, okay? So now as we are going to find the mass, so we rearrange it, then the mass will be equals to moles times the mR. So simply, first of all, you are going to find the mR of the ammonium iron 2 sulfate dot 6H2O. How? You can easily see how many nitrogen atoms we have. 2 times 14 plus 8 times 1, which is the atomic mass of hydrogen, plus 1 iron, which is 55.8, plus we have 2 sulfur, so 2 times 32, plus we have 8 oxygens, 8 times 16, plus we have 6 water, and the molecular mass of the water is 18. What should be the total mass? I'm going to do it. So 14 times 2 is 28, plus 8 plus 55.8 plus 64, and then plus 8 times 16, and then plus 6 times 18, okay? So what should be the final answer? The answer is 391. The answer is 391.8. So this is the mR. We calculated the moles above, okay? So the mole was 2.5 times 10 raised to the power minus 3. Remember that as in this compound the moles of the iron are 1, mean exactly 1 mole of iron. So we got from this, so it means if we are taking 1 mole of iron, we have to take the 1 mole of the whole compound. So that's why the moles remains the same. So now moles multiply by the molar mass, which is 391.8. so I'm going to multiply it by 2.55 multiply by 10 times raised to the power minus 3. So the final answer which I got is 0.99, okay, 0.99, which we can say approximately 1 gram. So remember that this is based on my calculation and my readings, okay? So it may be differ according to your values. Understood that? Now along with I'm going to discuss some of the, again, a basic question that are asked in previous exam related to the this type of a titration, and those are, I'm just going to show you like this, okay? So some of the related question I'm going to discuss here. He says that this is the same question but slightly little difference type of the calculation, but the question is exactly the same. The question is exactly the same. You can see here. This was the main question: ammonium iron 2 sulfate, Fp1, and but we have potassium manganate to titrate it with. Okay, so now just focus. Okay, now same method you have to adopt here. It requires some dilution method, and what I said, do as directed. Whatever the examiner is advising you, just do it. Okay, try not to do any different step that is not advised and you did. Okay, just follow the instructions. So this was the same question but slightly difference. what was the purpose to show this? The purpose to show this type of the question is that I'm going to solve some of the related questions like this. He says that a student learns that the solution of iron 2 salt has been prepared by dissolving the solid in distilled water that has absorbed air from the laboratory. Suggest a way in which the distilled water can be prepared and stored in the laboratory to ensure that it contains a minimum of dissolved air. So one of the best method is that store the solution in any bottle or container that has no space between the lid and the liquid level. Okay, so for example, if you have a situation like I'm going to show this over here. For example, you store this in a bottle like this. Okay, so this was the bottle in which you prepared the whole sample solution. And if your solution level is here and there is a gap between the tap, between this tap and the water, so you can easily say here air is trapped. So from this air, oxygen can easily be dissolved into the solution. Oxygen can easily be dissolved into the solution. So one of the best way to avoid this situation is to not generate or create any gap between the lid of the bottle like this. So you must have to fill the solution like this over this level. Okay, so it should be like this level and you left nothing, any space here, so that no air should be there. No air should be there. When there is no air, we can easily say that no oxygen from the air should or could be dissolved in the solution. So this is the one of the method. Second method is that keep the solution warm. Keep the solution warm, because on heating or on higher temperature, dissolved gases or the solubility of the gases in solution decreases. Solubility of the solution decreases when we have a hot solution. So keeping these two ideas in your mind, you can easily answer the question. What was the question? That how to avoid the dissolving of the oxygen into the solution from the air. Okay, so these are the two simplest suggestions. Next, he says that estimate the error in adding a volume from a burette. Okay, so remember that the minimum value is what we can say 0.05. 0.05. Let me, because I am unable to write here, I'm just going to copy so that you can easily see what I'm going to do. What you are going to do here, he says that 0.05. This is the minimum or the smallest division over or on the burette. You can easily see that you can measure this volume very easily. Then he said estimated error. This is the estimated error. Sometime you may round it off to the next figure, or sometime you may round it off to the previous figure. For example, in the burette we have the reading. For example, this is 10 and here we have small readings, okay, like this 1 2 3 4 5, like small reading, and the level of the liquid is, for example, over here in between these two. So you may have to round it off exactly 10, or you may round it, or you may have to write it as 9.05. okay, so in this way there is a chance of an error. So you may go to the upward direction causing a plus error, you are going to the downward direction causing it to this is the exact value. Sometime you may write it as 10.0 or 9.0, okay, 05. So there is a chance of error adding or subtracting of 0.05. Remember that 0.05. So this is the error. Now he says that what is the maximum possible error in obtaining a tighter reading. So as I clearly mentioned, sometimes you ignore that tiny 0.05 value and goes to the next value, that 10.0 0.01. Okay, so or sometimes you may go down. So the minimum reading is actually the error. So this is 0.05. Understood? And then this is called as the estimated maximum error in the titer, multiply by 2. This is the error, and we read the burette twice for the final and the burette reading, initial readings, and then divided by the titer. Okay, the value, the value you obtain during the titration. When you do this, you got the final answer. And the titer in this case you have to take according to your readings. Understood? So you just have to keep this formula in your mind. How to calculate percentage error is the what we can say the least count of the equipment we used, multiply by the times, how many times we use that equipment to measure that volume, and then divided by the value or the reading. Okay, so this should be the reading. Going for the next question, he says that during one titration a student reads the burette twice. Each reading has an error, but the titer has no error. So how it could be done? In simple way, we can say that first time initially, let we expose that while taking the initial reading, student do a positive reading and added 0.05 more, okay, plus reading. And then when he was taking the second reading, the final reading, he do the same mistake but in opposite direction, -5. So this error cancel out the previous error. So we can say that the errors in opposite direction, there is a chance that there is an error which was in opposite direction which cancel out the effect of each other, and hence overall there was no error. Although there was an error of taking both of the readings, but the error is cancelling the effect of each other, and the final reading has no error at all. So these are some possible, what we can say, the situation which we must have to discuss. Okay, so hopefully you understand how to solve these type of the questions. Try your best to find out these type of the reaction in your previous exams and try to solve all those one by one. If you have any question and you want to discuss with me, you can ask me in the comment section. Take care of yourself. Wish you best of luck for your exams. Stay safe, stay healthy. We'll see you in next video.